I'm feeling adventurous today on your own behalf. Just to get us going here, can we try? I got the integral from 1 to 2, 1 minus x squared e to the 3x. See what you think. If you need a little refresher, talk to your friends. Or ask me, I'll be walking around. Maybe I will refresh your memory about the integration by parts formula. It is integral u dv is uv minus integral v du. We said something at the very end about how to handle the integration boundaries in integration by parts. Take a glance at your notes from last time if you've forgotten. Or ask me, I'll tell you. Feel free to chat with your friends about it.
I what that was. Yeah, I remember it. Sorry.
You know what you consider that?
Yeah, you just do it again, right? Yeah, I did.
How's it going here? This looks good. Yeah, and then here is the new parts again. All right. Still good? Since they're multiplied here, because of yes. Because the whole thing is a definite interval brings the answer is it ought to be in the area of something, right? So you better plug it everywhere or else there's like an excess answer.
All right, can we do this one? Folks seem to be doing all right. This one takes a few minutes. You got to do the parts twice, and that sort of the tip off to that is that I have a quadratic here. Generally, every time you do the parts, the polynomial part will reduce in degree by 1, and so after doing it once, you end up with a like just x to the power 1 in that part, and then you do it again, and that part goes away entirely. So my first time through at least will be, that's the u, and then for the dv I use e to the 3x. The du is negative 2x dx, and then the v, sorry I should have put dx with the dv. The v is the integral of that, which is 1 over 3 e to the 3x. I hope everybody remembered this is a handy thing to memorize. The integral of e to the kx is 1 over k e to the kx, and that's what I just used in that step right there. So here I go, uv minus integral v du. This is, I'll write it, uv minus integral v du. So I go 1 minus x squared, that's the u. V is 1/3 e to the 3x minus integral v, 1/3 e to the 3x. Du is times negative 2x dx. Simplify a little bit, I suppose you could pull out 2/3 from this, or negative 2/3, we'll make that a plus, and then what remains will be x and e to the x, and that's what I'm going to do parts again with. Maybe I'll just write that. 1 minus x squared, 1/3 e to the 3x, and then it's going to be a plus 2/3 integral x e to the 3x. Right? And now I do parts again right here. X times e to the 3x. U is x this time. Du is just 1 dx. And dv will again be e to the 3x dx. V will be the integral of that, which is 1/3 e to the 3x. And then do my parts formula again. We're almost done here. It seems like it's hot again in here. Is that true? We had like one day where it was, I don't know about perfect, but tolerable at least. All right, and now inside these parentheses, parts one more time. uv will be x times 1/3 e to the 3x, and then minus integral v du. That's 1/3 e to the 3x. Du is just dx. All right, and then one more
step where we integrate. Plus 2/3 x times 1/3 e to the 3x minus, okay, this is 1/3, and then another 1/3 e to the 3x. And at this point, if it were an indefinite integral, I would put the plus c, but this one was a definite, which I've been ignoring since then, but at the very beginning, it was integral from 1 to 2. So right here, I plug 1 and 2. And you plug the 1 and the 2 in everywhere for x, not just for like the most recent part that I did. You have to plug it everywhere for x because, after all, the answer is supposed to be just a number. Because it's a definite integral, it equals some number. And so you cannot leave x's in your answer at the end. You have to plug these in for x's everywhere. So my final answer, 1 minus 2 squared times 1/3 e to the 2 plus 2/3, 2 times 1/3 e to the, sorry, I wrote e to the x. This e to the x right here should be e to the 3x. That was a typo. So it's e to the 3 times 2. Another e to the 3 times 2 minus 1/9 e to the 3 times 2. Okay, that's what I get when I plug in 2 everywhere, and then I go minus, and now plug in 1 everywhere. There should be parentheses around this part. 1/3 e to the 3 plus 2/3. 1 times 1/3 e to the 3 minus 1/9 e to the 3. Like that. I think that'll do it. If you want to be crazy, you can try and simplify that in terms of a bunch of e to the 6's and a bunch of e to the 3rds. I don't care about none of that. All right. Anybody thoughts about that one? I hope that went all right for you eventually. This one's kind of long-winded, but not a whole lot to it. All right. All right. Now that our memories are all refreshed, I got one more example with parts, and then we'll move on to something completely different. This is an especially weird one, extra weird one. I probably wouldn't ask you to, well, I definitely wouldn't ask you to do this on the quiz because it involves a very strange step. But I just wanted to show sort of how integration by parts can be used in sometimes weird ways. Let's try integral of e to the x sine of x dx. All right. I'm going to choose my parts. Now I have to choose the u and the dv. I have e to the x and also sine of x. You should think about, you want to choose the u to be one which gets simpler when I take the derivative, although that's not really true of either of those. E to the x, the derivative is the same. Sine of x, the derivative is cosine, which might as well be the same in terms of like how complicated it is. And I would say also the same is true of the dv. Like neither of those changes much when you take the antiderivative either. It turns out actually in this example it doesn't really matter how you choose it. So I'm just going to do u equals e to the x, dv equals sine x dx. This one actually you can do it either way around and you will get the same answer. But anyway, let's do the rest of it then. So u is e to the x, du is also e to the x dx. And then v is integral of sine x dx. Integral of sine is negative cosine. So this is minus cosine x. All right. Do my parts formula, uv minus integral v du. So this equals u e to the x. V is negative cosine x minus integral v minus cosine x. Du is e to the x dx. All right. Those minus signs can combine plus integral sign, but then otherwise you can't do much to simplify this. Maybe I'll just beautify this a little bit. Minus e to the x cos x plus integral e to the x cosine x dx. All right. Did this integral get any simpler? That's what you should ask yourself after doing the integration by parts. We had e to the x sine x. We now have e to the x cosine x. The answer to my question, did it get any simpler? No. I mean, it's different, I guess, but it's
It's not very different, right? The sine is now a cosine. Ordinarily, you should be a little dismayed at this point, but this is a weird one. Let's see what happens if we do it one more time. So I'm going to do the parts again, and I'm going to make the same kind of choice. So u equals e to the x, and du equals, or dv this time is cosine x dx. So let's do it again. U equals e to the x. dv is the cosine x dx part. So that means du is e to the x dx. And the v would be the integral of cosine x, which is sine x, without the negative, right? Okay, let's do it. So this is now minus e to the x cosine x plus, and here I'm going to do uv minus integral v du. So u is e to the x, v is sine x, minus integral v sine x du e to the x dx. All right. And again, we should think about comparing to what we started with. Actually, now we've sort of gone full circle. We have now exactly what we started with, which perhaps will make you think this has been a whole waste of time. It's actually not quite been a whole waste of time. I don't know how you feel about this class in general. I hope you do. But so I'm going to beautify this a little bit, and let's just write the whole thing. Where we started was integral e to the x sine x apparently equals this stuff. Minus e to the x cosine x plus e to the x sine x minus integral. I write the e first. I like writing the e first. Like that. All right? And now, like I said, we should feel kind of defeated at this point because I just ended up with what we started with before. Although, all is not lost. Anybody have an idea of what can be done here? Actually, we are not defeated. In fact, we are pretty much done at this point, if you think of it in a certain weird way. Any idea? You got an idea? Yeah, this is the same thing that we started with, but it's subtracted, right? That means we can add this on both sides. Okay? Okay. So it'll be, on the other side, it'll be now two of them, right? We're add integral e to the x sine x dx on both sides. And the left side now will say 2 integral e to the x sine x equals this here. How do you like that? This is actually kind of the answer, right? We can just divide both sides by 2, and that'll do it, right? Very strange way of ending up with the answer, but what you see on the right-hand side here has no more integral signs, which means we have actually calculated the antiderivative. So I'm going to divide both sides by 2. It's prudent, I would say, probably right at this point to put a plus c, because this integral is that, but it could possibly differ by a constant. This is slightly weird, but it's really because you don't need the plus c at this point because I have an integral on both sides, and either one could differ by an extra constant. Here we have the integral only on one side, and you have to put the extra constant somewhere, so I put it there. So anyway, the final answer, this really is the answer, e to the x sine x dx is, I'm going to divide both sides by 2. Put 1/2 in front of everything on the right side. E to the x cosine x plus 1/2 e to the x sine x plus c. There you go. You could say 1/2 c, but c represents any constant, so 1/2 c is the same as c. All right? So this is a weird, extra, little tricky step at the end. You really only do this in an example where you worked the integration by parts several times and end up with the exact same thing that you started with, and then you can do this weird trick at the end. This is a rare thing. Like, it usually doesn't work out like this, but like I said, I just wanted to show an example of how something a little strange can happen. All right. This is the last of the integration by parts that I wanted to discuss. Now we are on, this chapter in the book is all about different tricks for the integral. So far as your bag of tricks, we have the u substitution, the integration by parts. Let's talk about another one. We have, I guess, 3 more from this section that we're going to do. And actually, the next 1 or 2 here are, in my opinion, maybe the hardest of the integral tricks that we're going to do this semester, and maybe the hardest thing ever that we're going to do this semester. So get ready for that. Put on your thinking caps, as they say. This section is called trigonometric integrals. I don't know if this is something that you've seen in high school. I know a lot of you have seen most of this stuff. I know I never did this in high school, so this may be new to some folks. Although I wasn't especially, I wasn't like a math genius when I was in high school. I didn't realize I was good at math until I was in college, because I was never very good at like adding and multiplying numbers. And so my teachers, when I was a kid, always thought that I was bad at math. But like real mathematics is not about adding and multiplying numbers. So like eventually I realized that I was, whatever real math is actually about, I am actually good at that. I'm just not good at like adding and multiplying numbers in my head. Anyway, trigonometric integrals. So this is special tricks for evaluating things that look like this. Here's an example. Cosine to the 4x, sine cube of x. All right? So what we're going to be talking about in this section is products of powers of sines and cosines. And I hope everybody knows when you put the 4 there, this like cosine to the 4, of course, what that means, this is the same as this, cosine x to the power 4. Sine cube x means sine of x, the whole thing cubed, right? It's just a weird way that people write things. Actually, I don't really like writing things in this first way, but it's totally standard. And in our book, everybody, even outside of our book, always writes things like this. Really, what it means is that if I had my way, everybody would write it this way because I think it's a lot clearer. But I'm not gonna argue, so I'm gonna write it that first way also. All right, these are integration tricks for doing integrals of products of trig functions. This is like a sort of a hyper-specific trick. It only works for this kind of thing, and this is called a trigonometric integral. But actually, these trigonometric integrals appear often, and often they appear in settings where you wouldn't expect them to appear at all. So sometimes you'll start with something which actually doesn't look anything like that, but eventually you will realize it turns into one of these. Anyway, the tricks here actually are based just on U substitutions done in a very strange way. So I will say the tricks are based on U substitutions together with formulas about trig functions. In particular, this one, which I hope everybody knows, this is the most important of all of the trig formulas that you ever learned, other than, I suppose, like the definitions, the SOHCAHTOA thing. This is the most important of all of the trigonometric identities. Based, I said based, I meant to say based on. These tricks are based. That's what people say on the internet now. And I'm not sure what that means. It means like I like it and I'm a MAGA guy. Is that what that means? I feel like based is only used by sort of right-wing white American bros. Is that true? I don't know. This is the impression I get.
Never heard that before.
No?
I've never heard that word.
Oh, okay. Are you a white-ring American bro? No. Maybe that's why. Yeah, I don't know. Anyway, so that one, and also one more is this one ends up being important. There's one for the sine of 2x, and it's this. This is an obscure one, which I would say in general there's no compelling reason why anybody should know this formula, but for the sake of doing trigonometric integrals, this one comes up a lot. And similar, there's one for cosine. Cosine of 2x. 1/2 1 plus cos 2x. This is weird. This is not a typo. It really is cosine for both of them here. One is a minus, one is a plus.
Does it only work when it's 2, or can you, like, if it's 3x?
This 2 here?
Like, if it was cos of 3x, would it be like 1/3 plus 1?
No.
Or would it only work?
Yeah, this is only true with a 2 there. Although if it's, there are variations with a 3, but it's not so simple. Yeah. All right, and also what I'm sorry. This, did I say it's not a typo? There are typos here. This is not sine of 2x, it's sine squared of x. And it's cosine squared of 2x, sorry. That's important. Like that, all right? Sorry for my typo. Okay, and also, one more thing, everybody knows, of course, the integral of sine is cosine, negative cosine. If you have an extra constant on the inside, it works just like the extra constant on the inside of each of the x. So these will come up also. The integral of sine kx is 1 over k, negative 1 over k cosine kx, and the integral of cosine kx is 1 over k sine kx. All right. These are just the ordinary integration formulas for sine and cosine, only with an extra constant on the inside. You will see when we do this trick, it ends up creating extra constants on the inside fairly often. It's actually because of this. If you start with a sine squared, you can turn it into this, which is a cosine, but with an extra 2 on the inside. All right, so all of these, I suppose you should memorize. I mean, we're going to do these problems enough that hopefully you will remember them without much effort, and you kind of already know some of these. I would say the ones that I'm likely to forget are really these two. The rest of them, I hope, are very familiar to everybody already. All right, let's just try some of these tricks. So let's do, actually the example that I wrote at the beginning, I don't want to do just yet, but let's try integral of just cosine cubed of x dx. All right. We're going to do this using a weird u substitution. And the idea here is, here's the idea. I want to do u equals cosine x. Because that's cosine of x cubed, right? And so it would be natural to choose the thing on the inside of the cubing to be my u, but this is not going to work as is because the du is negative sine x dx, and I don't see anything like negative sine x over there, all right? And the trick here is, the du doesn't work. Instead, what I want to do, let me just write this. I want to do u equals cosine x, but the du isn't in there, right? The du in that case would be something about sine of x, and I just don't see any sine of x over there at all. All right, here's the real idea. This is sort of the strategy that we use here. Strategy. And I have a name for this strategy. It's called the save one strategy. The idea is I'm going to save one cosine. Actually, you can do this by saving one, in this case I have to save one cosine x. And then turn the others into sine x, all right? And so, this is a weird trick, but I'm going to write cosine cube x as cosine squared x, and then another cosine x. This is the one I saved, right? I'm going to save one of them, and then on the other ones, I'm going to turn them into sines by using the everybody's favorite trig identity, this one here, all right? So this here, we can solve for cosine squared. It'll say cosine squared is 1 minus sine squared, and that I'm going to plug in right here. So this will say 1 minus sine squared x cosine x dx, all right? Cosine squared is the same as 1 minus sine squared. A according to the very first of those trig identities, the one that everybody knows. And then you plug it in there. All right, and what's so good about that? Now I can do a u substitution. That's kind of the point of all this. Now do, but I'm not going to do cosine. Actually, I'm going to do u equals sine of x. Du equals cos x dx. How you like that? Now this does actually have the du that I want, all right? Because I saved that one. That's why I saved one, so that it would become the du later on, all right? So my substitution then, I see integral, so this here, writing the substitution, 1 minus u squared du. Ain't that nice? Now this is an easy integral to do. All right, it used to say 1 minus sine squared x, but u equals sine of x, so that's u squared. And then the rest of it, cosine x dx, is that is du. All right, this is a weird trick. This is the end of the weird trick. From here, it's just an ordinary integral to do. So I just integrate here. 1 becomes u minus 1/3 u cubed plus c, right? And then replace the original variable. U equals sine x. So my final answer is, oh, come on now. No. All right. U equals sine x. So sine x minus 1/3 sine cube x plus c. This is the answer. All right. So when you see, I'll try to summarize the trick here. If it's, say, cosine of maybe, I don't know if I need to summarize it. We save one and then rewrite the other ones in terms of sine squareds or cosine squareds as appropriate. Let's try another one. You'll get the idea, I think. How about integral sine squared x cosine to the 5x dx? All right, that one that I did was an easy one. They can get more complicated. I am again going to do the save one trick. It will either be save one sine or save one cosine. Actually, it has to be save one cosine if you think about how this works. I'm going to do save one cosine. And this is sort of a general principle. The one you save should have an odd power. You'll see in a moment why that's necessary. But the reason I'm going to save one of the cosines in this case is I can tell cosine to the 5, that's an odd power. And the other one is an even power. All right, so my strategy will be save one cosine and then write everything else. Write all others using sine. All right? Just like we did before. We saved one cosine and then turned everything else into sines. I'm going to save one cosine and then turn everything else into sine. Now, some of it already is sine, but there's going to be other ones too. So when I do the saving one cosine, it looks like sine squared x and then cosine to the 4x, and then here's my one saved cosine over there. And now I want to write everything else using sine. All right? Express these as sine x. And how do we do that? Well, sine squared x is already okay. I want to use sines rather than cosines. Cosine to the 4x we need to deal with turning it into somehow sine of something. Anybody have an idea with this? Just a simple variation from before.
Can't you just break them up into cosine 2x and then write them as 1/2 1 plus cosine 2x?
You can. So I liked your first idea, and your second idea I think wasn't wrong, but there's a nicer way to do it. I want to think of this as cosine squared. I think she said it's like a cosine squared and another cosine squared, right? But actually, it's good enough to just write it like this. Right? It's a cosine squared. That's what cosine to the 4 is.
And then what can we do with cosine squared? Actually, we can do one of those rules up there. Now, I think she said do this one, but actually, it's better to just use this one. Cosine squared is 1 minus sine squared, right? These other ones don't come into play just yet in this trick. So that cosine squared, I write as 1 minus sine squared, like that. All right. I have expressed the rest of it as a stuff in terms of sine of x. It is important that you'll see why now this trick, what I just did with cosine to the 4, this will only work if that exponent is even, because it requires that you turn cosine squareds into sine squareds. If this was, say, cosine to the 3, it wouldn't work, because you wouldn't be able to split this up as 2 cosine squared, so you'd have like an extra cosine left over. So that's why this thing I said in the red is the case. The one you save should have an odd power. That's so that cosine originally had an odd power. You pull one of them out, then what remains is an even power, and then you can do this to it. All right? If it wasn't an even power, you wouldn't be able to do that step. Anyway, now we do the substitution. This is very strange looking, but it's about to get much clearer. U equals sine x, du equals cosine x dx. And when we plug this business in, it all gets very simple, or at least simpler. U squared, 1 minus u squared, squared. And then cos x dx is just du. All right. Is this simple now? I would say kind of. How should we do this integral? Yeah? Distribute, yeah. I would do like the FOIL of that big squared, expand that into something, and then distribute the u squared across it. So here at this point, it's just a weird looking polynomial. We can do the FOIL on that second part here. It shall be 1 minus 2u squared plus u to the 4, right? That's the FOIL over there. And then distribute u squared across that whole thing. U squared minus 2u to the 4. I'm adding exponents here, plus u to the 6. Do you agree this is a weird trick? I feel like it is. All right. But anyway, do the integral now, right? This is an easy integration to do. I go 1/3 u cubed minus 2/5 u to the 5 plus 1/7 u to the 7 plus c, and then finally plug back in. The original variable was u equals sine x. So my final answer, 1/3 sine cube x minus 2/5 sine to the 5x plus 1/7 sine to the 7x. That's that. All right. Any thoughts about that one? Other than whoever came up with this and why you making me do this? These are questions that are hard to answer. I actually don't know who came up with this. It really, like from an abstract point of view, it's just U substitution. It's just in a pretty strange way, in my opinion. All right. Great. Could you all try one? I got one for you all to try. So let's just see how it goes. Sine cube x, cosine cube x. All right. Now in this case, like I said before, the one that you save ought to be one which has an odd power in it. Now this one, both of them have odd power, so actually it's possible to do either way around. You can choose to save one of the sines, or you can choose to save one of the cosines. Maybe just for the sake of, just because it's complicated, just so that we all do it the same way. Can we decide all together? Let's save one of the sines. So I'm going to, as the first step, write it like this. So this over here is the one sine that I saved, and what remains is this stuff over there. And the idea is you save, in the previous examples, I save a cosine and write everything else using sine. In this one, I save the sine. I'm going to write everything else using cosine. See what you think. Express the rest of it using cosines. A lot of it is already cosines, which you can just leave like it is. Everybody's looking good. Let's just do this one. I think that'll probably do us for today. So we save one sine x, and then in the rest of it, I'm going to write sine squared x as 1 minus cosine squared x. Like so. And then my substitution is u equals cosine x. du is negative sine x dx. Now there's a negative here inside the integral. I don't see negative sine x, so when I do my substitution, you have to insert an extra minus sign
which you can just factor out of the integral anyway. So after the substitution, it's this. I hope that's what you got after the substitution. All right? And now we have to do the integral. You can just distribute u cubed and then integrate everything. So it's minus integral u cubed minus u to the 5 negative 1/4 u to the 4 minus 1/6 u to the 6. Put my plus c, and that's that. So u is cosine x, so it's cosine to the 4x minus 1/6 cosine to the 6x. Like that. This is the first of the trig substitution tricks. So I will just reiterate, do this when at least one power is odd. All right? Actually, if they're both odd, it's okay. This one that we just did, they were both odd, and it still works. If they're both even, you got problems, though. Because if they're both even, when you save one, the stuff that is left over has an odd, but the stuff that you're going to have to re-express that one in terms of the other variable. So when both are even, use a different trick. And do you mind a cliffhanger? This is what we're going to talk about next time. So you'll be in suspense all weekend. When both are even, it's a different trick, and the different trick is based on the other formulas that are at the beginning, cosine of 2x, those things. All right. So you shouldn't use those other ones for when one of them is odd. When both are even, it's something else.
And so for the homework